All right, so this is lesson 110, part B, limit of composite functions. These are composite functions. The limit as x approaches a of f of g of x is equal to f of limit as x approaches a of g of x. So we kind of put it in, evaluated the limit as x approaches a of g of x. We've done this before, provided that the limit exists. We already done this already in prior lessons. And let's review. And it has to be that this is so very important that f of x is continuous. It has to be continuous at x equal to L, or else you cannot use this definition. So let's do one. Consider the graphs of the function f of x and g of x given below to find the following limits. So you got these two functions, f of x, g of x. Let's evaluate problem 6. The limit as x approaches 1 of f of g of x. So we'll just go ahead and apply the blindly. Let's apply it. Let's just do it. The definition. So we just go f parentheses lim x approaches 1 of g of x. So let's go ahead and find the limit as x approaches 1 of g of x. Let's do this. Limit as x approaches 1 of g of x. We're talking about this one here as x approaches 1 here. So as we get closer and closer, is 0. The limit is 0. So now we're going to go f of 0. F of 0 is 2. So everything's good. This function is continuous here. This function is continuous here. There's no problem. The answer is 2. The answer is 2. Now, this is where it breaks down. I'm going to tell you already. Let's blindly follow this g of lim x approaches 0 of f of x. So let's go ahead and do the limit as x approaches 0 of lim x approaches 0 of f of x. So as we get closer to 0, the limit is 2 here. So we're going to think about just going g of 2. Evaluating g of 2. Let's see, we get closer and closer to 2. We got a problem here. There's a jump discontinuity. And we can only apply the rule if it's continuous for both functions. And the second function is not continuous. So what we're going to do is retract. And we're going to go back over here to where we came from. See all these inputs here? Let me do this again. Look, all these inputs from the left and from the right are coming from the bottom, from smaller numbers. See, these outputs are getting so we're coming from below. So we're coming from below, meaning that over here on G, we're coming from the left. So we're going to have to evaluate coming from the left here. So because there's a jump discontinuity here, we're only going to come from the bottom, meaning from the left here. And so the answer to this limit is 3. So that's how we do these kind of problems. Okay, let's do problem number 8. Find the limit as x approaches 0 of g of f of x. Let's go ahead and apply that limit rule for composite functions. G of lim x approaches 0 of f of x. Find the limit as x approaches 0 of f of x. So we're coming here, and from here. The limit is 0. So we're going to go g of 0 This is continuous. We got no problems whatsoever here. We go to G of 0. This is G. And we got a problem of jump discontinuity again. So we got to go back again where we started. And the function actually, it's coming from the top. It's coming from the top. That from both the left and the right, it's coming from the top, meaning that we're coming from the right. Inputs are coming from the right for G, so it's coming from the right only, and so the limit will be 2. So this is going to be 2. Let's go over the third case of limits and the types that do not exist. Lim x approaches 0 of sine 1 over x. So we had jump discontinuities. We had other ones. Which one were they? There were 2 that we had already gone over. But this is a third case of a limit that does not exist. Let's do this middle one here. The limit as x approaches 0 from the left of sine 1 over x. So let's apply the composite function rules. Then we do the limit as x approaches 0 from the left of 1 over x. And you'll remember 1 over x goes like this. So as we approach from the left, we approach 0, the function is going to negative infinity. Negative infinity. So these there is numbers that we keep going, getting closer and closer to 0. It will get really negatively big, like negative 1,000, negative a billion, negative a gazillion. But it keeps going forever. And when you take the sine of some number, sine of a number, sine is a function that goes forever as well, oscillates between 1 and negative 1. So the function of sine goes forever like this. It goes forever like this. So you will always be putting this time negative numbers. So it wouldn't be here. You would be going that way. And it will always be oscillating between negative 1 and positive 1, negative 1 and positive 1. And it will never reach a number, a final answer. It just oscillates. Same thing will happen to this one. We apply the rule. So we apply the composite function rule. And the same idea that I gave there, it would oscillate also from negative 1 to 1 as input values approach 0 from the right. And so this does not exist. And so this is what it looks like. When you graph sine 1 over x, it looks like this. And then it just oscillates up and oscillates. So when it oscillates, there's no final limit number that it approaches to. So this is the third case of a limit that does not exist. It's an oscillating limit. Okay, see you next time.